Welcome to Sleepless Astronomer, where we explore the wonders of space and the universe. If you're enjoying these cosmic journeys, please like this video and subscribe to the channel. We post new videos every single day, so you can tune in whenever you want to learn about the cosmos. And we'd love to hear from you in the comments. Let us know where in the world you're watching from. We always enjoy connecting with fellow space enthusiasts around the globe. Now let's begin tonight's journey through the universe. The zone where life could exist. Life as we know it requires certain conditions to exist. Too hot and water boils away. Too cold and water freezes solid. Without liquid water, life as we understand it cannot survive, at least not the kind of carbon-based, water-dependent life that evolved on Earth. This simple requirement creates a critical region around every star called the habitable zone, sometimes nicknamed the Goldilocks zone because conditions there are neither too hot nor too cold, but just right for liquid water to exist on a planet's surface. Understanding this zone and what makes it special reveals both the requirements for life and the astonishing variety of places in the universe where life might possibly emerge. The habitable zone is not a single precise distance from a star, but rather a range of distances, a band extending outward from the star where temperatures allow water to remain liquid. For our Sun, this zone extends roughly from about 90 million kilometers to about 150 million kilometers from the Sun. Earth, orbiting at about 150 million kilometers, sits comfortably within this zone, though closer to the inner edge than the middle. Venus, at about 108 million kilometers, orbits just inside the inner edge, where temperatures are too high. Its surface temperature exceeds 450 degrees Celsius, hot enough to melt lead, far too hot for liquid water. Mars, at about 230 million kilometers, orbits near or just beyond the outer edge, where temperatures are generally too cold. Though liquid water might occasionally exist in certain locations under special conditions. The boundaries of the habitable zone depend entirely on the star's properties. Hotter, brighter stars have habitable zones located farther out because their intense radiation heats planets to higher temperatures. Cooler, dimmer stars have habitable zones located much closer in. A red dwarf star, the most common type of star in the galaxy, might be only 1/10 as luminous as the Sun, meaning its habitable zone would be about 1/3 the distance from the star. A planet orbiting in the habitable zone of a red dwarf might orbit only 10 million kilometers from its star, closer than Mercury orbits our Sun, yet still maintain temperatures suitable for liquid water because the star is so much dimmer. The habitable zone also depends on the planet's atmosphere. A thick atmosphere with greenhouse gases can trap heat and keep a planet warm even if it orbits farther from its star than the outer edge of the simple, habitable zone. Venus demonstrates the opposite effect. Its extremely thick carbon dioxide atmosphere creates a runaway greenhouse effect, trapping heat so efficiently that surface temperatures soar far beyond what you would expect from Venus's distance from the Sun alone. Without this greenhouse effect, Venus might be cool enough for liquid water. With it, the planet is an inferno. Mars provides another instructive example. Mars orbits near the outer edge of the Sun's habitable zone, and its thin atmosphere, less than 1% the pressure of Earth's atmosphere, cannot retain much heat. Surface temperatures average around -60 degrees Celsius, far too cold for liquid water most of the time. But billions of years ago, Mars had a thicker atmosphere and likely had liquid water flowing on its surface, creating the river valleys and lake beds that spacecraft have photographed. Mars lost most of its atmosphere over time, probably because its weak magnetic field couldn't protect the atmosphere from being stripped away by the solar wind. The planet moved out of effective habitability not by changing its orbit, but by losing the atmosphere that kept it warm. Earth maintains liquid water on its surface through a fortunate combination of factors. Our distance from the Sun provides a baseline amount of heating. Our atmosphere, with modest amounts of carbon dioxide and water vapor, acting as greenhouse gases, traps enough heat to raise the surface temperature by about 33 degrees Celsius, above what it would be without an atmosphere. Our magnetic field, generated by the liquid iron core's motion, shields the atmosphere from the solar wind, preventing the atmospheric loss that doomed Mars. Our planet's size gives it enough gravity to hold onto its atmosphere over billions of years. But the habitable zone is more complex than just distance from a star and atmospheric composition. Other factors influence whether life could actually emerge and survive. Planetary mass matters. A planet too small cannot retain an atmosphere because its weak gravity allows atmospheric gases to escape to space. A planet too large might have such a thick atmosphere that surface pressures become extreme, or might retain so much hydrogen and helium from its formation that it becomes more like a miniature gas giant than a terrestrial world. The planet's rotation rate influences habitability as well. A planet that rotates very slowly, or is tidally locked to its star, showing the same face always toward the star as the Moon does to Earth, would have extreme temperature differences between the permanent day side and permanent night side. The day side might be too hot for liquid water, while the night side freezes. Venus rotates extremely slowly, taking more than 200 Earth days to complete one rotation, though its thick atmosphere distributes heat efficiently enough that temperatures are fairly uniform across the planet, despite this slow rotation. Stellar variability affects the habitable zone's stability over time. The Sun's luminosity has increased by about 30% over its lifetime. Early in Earth's history, when the Sun was dimmer, Earth received less heat. Yet geological evidence shows that liquid water existed on Earth's surface going back nearly 4 billion years, despite the fainter Sun. This is called the faint young Sun paradox. The solution probably involves a thicker atmosphere with more greenhouse gases in Earth's past, compensating for the dimmer Sun and keeping temperatures warm enough for liquid water. As stars age, their habitable zones move outward. The Sun will continue brightening over the next billion years or so. Eventually, perhaps in 1 billion to 1.5 billion years, the Sun will become bright enough that even with our current atmosphere, Earth's surface will become too hot for liquid water. The oceans will evaporate, water vapor will accumulate in the atmosphere, and the increased greenhouse effect will push temperatures even higher in a runaway process. Earth will exit the habitable zone, not because Earth moves, but because the habitable zone moves outward as the Sun brightens. Subsurface habitability expands the possibilities beyond the traditional habitable zone. Moons orbiting gas giant planets can have liquid water beneath their icy surfaces, even if they orbit well outside the star's habitable zone. Jupiter's moon, Europa, and Saturn's moon, Enceladus, both have subsurface oceans kept liquid by tidal heating, the gravitational squeezing from their parent planets that generates internal heat. These moons demonstrate that life might not require surface liquid water or even a planet within the traditional habitable zone. The requirements might simply be liquid water somewhere, an energy source, and the right chemical ingredients. Tidal heating expands the possible locations for life significantly. A planet or moon doesn't need to orbit at a specific distance from its star if internal heat from tidal forces can keep subsurface water liquid. This might be particularly important for moons orbiting planets in the habitable zones of red dwarf stars, where tidal locking to the star might make surface habitability challenging, but subsurface oceans remain possible. The chemical composition of the planet matters as much as its location. Life requires more than just water. It needs raw materials. Carbon, nitrogen, phosphorus, sulfur, and trace amounts of many other elements are essential for the biochemistry we know. Planets that form too close to their star might lack volatile elements like carbon and nitrogen that are essential for life. Planets that form too far out and then migrate inward, might have compositions dominated by ices, rather than having the right balance of rock, metal, water and organics. Stellar type influences habitability in ways beyond just temperature. Red dwarf stars, while having habitable zones close in, pose challenges for life. These stars frequently produce powerful flares, sudden bursts of radiation, and charged particles that could strip away planetary atmospheres and damage biological molecules. A planet in the habitable zone of a red dwarf would need a strong magnetic field to protect against this radiation. Additionally, red dwarfs are so dim that their habitable zone planets likely become tidally locked, always showing the same face to the star, which creates the extreme temperature contrast problem. More massive stars, while having habitable zones farther out, present a different problem. They burn through their fuel quickly and don't live long enough for complex life to evolve. A star twice the Sun's mass might only live a few billion years before exhausting its hydrogen fuel and evolving into a red giant. On Earth, simple life emerged fairly quickly, within the first billion years, but complex multicellular life took nearly 3 billion years to appear. More massive stars might not remain stable long enough for complex life to evolve on their planets. Binary star systems where two stars orbit each other create more complicated habitable zones. If the stars orbit close together, planets might orbit far enough from both stars that the pair acts like a single brighter star, creating a habitable zone at a large distance. If the stars are widely separated, planets might orbit just one star in a habitable zone, determined primarily by that star's properties. But intermediate cases, where the stars are separated by distances comparable to their habitable zones, create complex and potentially unstable conditions for planets. The galactic habitable zone adds another layer of consideration. Different regions of the galaxy have different properties relevant to life. Near the galactic center, stars are packed more densely, and supernova explosions occur more frequently, potentially sterilizing planets with intense radiation. Far in the outer reaches of the galaxy, stars might be too poor in heavy elements to form rocky planets with the chemical complexity needed for life. The region where our Sun orbits, about halfway out in the galactic disk, might represent a galactic habitable zone where conditions are most favorable for life to emerge and survive long term. Exoplanet discoveries have found thousands of planets, many within their star's habitable zones. Proxima Centauri b, orbiting the nearest star to our Sun, sits within its star's habitable zone, though whether it actually has liquid water and a protective atmosphere remains unknown. Kepler and other missions have found dozens of roughly Earth-sized planets in habitable zones, though determining which of these might actually host life requires detailed atmospheric studies that current telescopes can barely begin to perform. The concept of habitability continues evolving as we learn more about the diversity of planetary environments. Life might exist in forms very different from Earth's biology, adapted to environments we would consider extreme. Subsurface oceans beneath ice shells, atmospheres of exotic chemistry on planets very different from Earth, even clouds in the atmospheres of gas giants. All these represent potential habitats that expand the zone where life might exist far beyond the simple band of distance where liquid water exists on a planet's surface. The habitable zone represents our best current understanding of where to look for life, based on the one example we have: Earth. It's a starting point, a place to begin the search, knowing that life's possibilities might extend far beyond this simple definition. The zone where life could exist might be much larger than we imagine, encompassing not just planets at the right distance from their stars, but moons with tidal heating, planets with exotic chemistries, and environments we haven't yet conceived, each one a potential home for biology waiting to be discovered. The glowing clouds, where stars are born. Scattered throughout the galaxy are vast clouds of gas and dust, some spanning hundreds of light years across. glowing with ethereal colours against the darkness of space. These nebulae are the cosmic nurseries, where stars come into being, regions where the raw materials of the universe, hydrogen and helium from the Big Bang, mixed with heavier elements forged in previous generations of stars, gather, collapse, and ignite into new points of light. Understanding these stellar nurseries means understanding one of the most fundamental processes in the cosmos, the transformation of diffuse gas into concentrated spheres of nuclear fusion that will shine for millions or billions of years. The process begins with the molecular cloud, a region of space where gas has accumulated and cooled to temperatures only a few degrees above absolute zero. These clouds are dark when viewed in visible light because the dust mixed with the gas blocks starlight from behind, creating dark patches against the background glow of the Milky Way. But observe them in infrared or radio wavelengths, and they reveal intricate structures, filaments, cores, and clumps where the density varies, creating a complex web of material threaded throughout these regions. Molecular clouds are mostly hydrogen, but at the low temperatures found within them, individual hydrogen atoms have paired up to form molecular hydrogen, H2. This molecular form is more stable at cold temperatures, and these clouds also contain molecules that might seem surprising in the depths of space: carbon monoxide, water, ammonia, formaldehyde, and even more complex organic molecules. The chemistry occurring in these cold clouds is rich and varied, with molecules forming on the surfaces of dust grains and in the gas phase, building up a diverse molecular inventory over millions of years. Something must disturb these clouds to initiate star formation. A cloud can exist in a stable state for a long time, with internal pressure from the gas supporting it against its own gravity. But if the cloud is compressed, if its density increases beyond a critical threshold, gravity begins to win. This compression can come from several sources: a shockwave from a nearby supernova explosion, pushing through space, the compression created when spiral arms of the galaxy pass through the region, or even the radiation and winds from existing massive stars that can trigger collapse in adjacent cloud material. Once collapse begins, the cloud fragments into smaller pieces. A single large molecular cloud doesn't collapse into one giant star. Instead, it breaks apart into hundreds or thousands of individual, collapsing cores, each one potentially forming a star or a small system of stars. This fragmentation occurs because as the cloud collapses, it develops instabilities. Regions that are slightly denser collapse a bit faster, pulling in material from their surroundings, and these growing density enhancements become the seeds of individual stars. Picture one of these collapsing cores. Initially, it might be 1/10 of a light year across, containing perhaps a few times the mass of our Sun, with a density barely above that of the surrounding cloud. As it contracts under its own gravity, the material falls inward, but it doesn't fall uniformly. The core rotates slowly, inherited from the overall rotation of the cloud, and as it contracts, conservation of angular momentum causes it to spin faster, just as a figure skater spins faster when pulling their arms inward. This rotation prevents all the material from falling directly onto the forming star at the center. Instead, material settles into a rotating disk around the protostar, a flattened structure where gas and dust orbit the central condensation. This is a protoplanetary disk, the structure from which planets will eventually form. The material in this disk gradually spirals inward, losing angular momentum through viscosity and magnetic effects, feeding the growing protostar at the center, while the outer portions of the disk may remain in orbit for millions of years. As the protostar grows, accumulating more and more mass from the infalling material, its center heats up. Gravitational potential energy converts to thermal energy as material falls inward, and the temperature and pressure at the core climb steadily. The protostar begins to glow, first emitting infrared radiation, then gradually becoming brighter as it contracts. At this stage, it's not yet a true star. No nuclear fusion occurs at its core, but it's radiating energy produced by gravitational contraction, a process called Kelvin-Helmholtz contraction. The infalling material doesn't simply accumulate smoothly. Young protostars are violent, turbulent objects. They generate powerful magnetic fields that interact with the surrounding disk and the infalling gas. These magnetic fields can launch jets, narrow streams of gas that shoot outward from the poles of the protostar at speeds of hundreds of miles per second. These jets plow into the surrounding molecular cloud, creating bow shocks where they collide with the ambient gas, heating it and causing it to glow. These glowing regions, called Herbig-Haro objects, appear as bright knots and filaments near young stars, moving visibly over periods of years as the jets evolve and push through the surrounding gas. The jets serve an important function. They carry away angular momentum and energy, allowing material in the disk to continue falling onto the protostar. Without this mechanism to remove angular momentum, the disk would simply spin faster and faster, and accretion would halt. The protostar continues to accrete material and contract for hundreds of thousands to millions of years, depending on its mass. During this time, it's deeply embedded in the cloud that spawned it, hidden from view at visible wavelengths by the cocoon of gas and dust surrounding it. Infrared observations can penetrate this obscuration, revealing the glowing protostar and its disk within the dark cloud. These embedded protostars mark the earliest visible stages of star formation, objects that are still gaining mass and have not yet ignited nuclear fusion. Eventually, the temperature and pressure at the protostar's core reach a critical threshold, typically around 10 million degrees. At this point, protons begin to fuse, creating helium and releasing energy through nuclear fusion. The protostar becomes a true star, entering what's called the main sequence, where it will spend the majority of its life fusing hydrogen into helium. The energy released by fusion creates an outward pressure that finally halts the gravitational contraction, and the star settles into a stable configuration where gravity and pressure are balanced. When the star ignites, it begins to affect its surroundings dramatically. The radiation from the young star heats the surrounding gas and dust. Ultraviolet light from the star ionizes hydrogen atoms, stripping electrons away and creating a region of ionized gas called an H2 region. These ionized regions glow with a characteristic reddish-pink color, the result of electrons recombining with protons and cascading down through energy levels, emitting light at specific wavelengths. This is the glow we see in many famous nebulae: the Orion Nebula, the Eagle Nebula, the Lagoon Nebula, vast regions of ionized gas illuminated by the intense radiation from young hot stars. If the star is particularly massive and hot, more than about 8 times the Sun's mass, it produces copious ultraviolet radiation that can ionize gas over large volumes of space. A single massive star can create an H2 region spanning dozens of light years. Multiple massive stars forming in the same region create even larger ionized bubbles. The Orion Nebula, visible to the naked eye as a fuzzy patch in Orion's sword, glows because of a handful of massive young stars at its center, whose radiation ionizes the surrounding molecular cloud. The radiation pressure and stellar winds from young stars don't just make the cloud glow, they also begin to push the gas away, clearing out cavities in the molecular cloud. This feedback can actually trigger more star formation in the surrounding material. As the expanding HII region compresses gas at its edges, it can push that material above the density threshold needed for collapse, triggering new rounds of star formation in a process that propagates through the cloud. Young star clusters often show evidence of sequential star formation, with the oldest stars at the center, surrounded by progressively younger stars farther out. The initial generation of stars alters the cloud, compressing and heating gas at the periphery, triggering the formation of the next generation. This process continues until the cloud is either dispersed entirely by the radiation and winds from the young stars, or exhausted of material dense enough to form new stars. The most massive stars, those dozens of times more massive than the Sun, live brief but spectacular lives. They burn through their nuclear fuel in just a few million years, and then explode as supernova, catastrophic events that briefly outshine entire galaxies. These explosions inject tremendous energy into the surrounding gas, heating it to millions of degrees, accelerating it to thousands of miles per second, and enriching it with heavy elements created in the star and in the supernova explosion itself. Carbon, oxygen, silicon, iron, and even heavier elements like gold and uranium. These heavy elements mix into the molecular cloud, changing its composition. The next generation of stars that forms from this enriched material will contain more heavy elements than the previous generation. This process of stellar birth, life, death, and rebirth has been occurring for over 13 billion years, gradually enriching the interstellar medium with heavy elements. The earliest stars in the universe formed from nearly pure hydrogen and helium. Stars forming today, including our Sun, contain about 2% heavy elements by mass, a small fraction, but crucial for the formation of planets, and ultimately for the existence of life. The dust mixed throughout these star-forming clouds plays a crucial role beyond just blocking light. The tiny grains, typically less than a micrometer in size, serve as surfaces where molecules can form. Hydrogen atoms landing on a grain's surface can find each other and bond, forming molecular hydrogen far more efficiently than they could in the gas phase. Water molecules, carbon monoxide, and more complex organics also form on grain surfaces, then evaporate back into the gas or become incorporated into forming stars and planets. Star formation is not perfectly efficient. Only a small fraction of the gas in a molecular cloud, perhaps 1 to 10%, actually ends up in stars. The rest is either dispersed by stellar feedback, ejected by stellar winds and supernova explosions, or simply never reaches densities high enough to collapse. The molecular clouds we observe are continuously evolving, with some regions collapsing to form stars while other regions are being cleared out by the very stars that recently formed within them. Different regions of the galaxy have different rates of star formation. The spiral arms, where gas is compressed as it enters these density waves, show enhanced star formation, lighting up with the blue glow of young hot stars and the red emission from H2I regions. The galactic center, with its extreme environment and powerful tidal forces, has intense star formation, but also extreme feedback that can suppress star formation. The outer regions of the galaxy, with less gas available, form stars more slowly. Star formation is occurring right now throughout the Milky Way and throughout the universe. In distant galaxies, billions of light years away, we observe intense starbursts where entire regions of galaxies are forming stars at rates thousands of times higher than in our galaxy, triggered by galaxy collisions or mergers that compress enormous quantities of gas. The stars forming in those distant galaxies emit light that has travelled across most of the universe's history to reach our telescopes, showing us star formation as it occurred when the universe was much younger. The glowing nebulae we see in telescopes and photographs are not static monuments, but dynamic regions of ongoing transformation. The clouds are collapsing, the protostars are growing, the newly formed stars are dispersing the clouds that gave them birth. Within a few million years, the blink of an eye on cosmic timescales, a star-forming region transforms from a dark molecular cloud to a bright cluster of young stars, to a dispersed association of stars gradually spreading through the galaxy, each one carrying forward the legacy of its birth, enriching future generations of clouds with the elements created during its life, continuing the cycle of stellar birth and death that has shaped the galaxy since its formation billions of years ago. The lighthouse stars that spin incredibly fast. In 1967, a graduate student named Jocelyn Bell noticed something peculiar in her radio telescope delta, a signal that pulsed with extraordinary regularity, repeating every 1.3373 seconds. The precision was so remarkable that she and her advisor initially wondered whether they had detected an artificial signal from an extraterrestrial civilization. They jokingly called it LGM-1 for Little Green Men. But as more of these pulsing sources were discovered, each with its own precise period, it became clear they were witnessing something natural, but entirely unexpected. Rapidly spinning neutron stars whose beams of radiation sweep across Earth like cosmic lighthouses. These objects, now called pulsars, are among the most extreme objects in the universe. They are neutron stars, the collapsed cores of massive stars that exploded as supernova, compressed to densities where a sugar cube-sized amount of material would weigh as much as a mountain. What makes pulsars special is not just their incredible density, but their rotation. These stars spin at rates that seem impossible for something so massive. Many complete one rotation in less than a second, some in mere milliseconds, whirling around hundreds of times per second while containing more mass than the Sun. The story of a pulsar begins with the death of a massive star. When a star, at least 8 times more massive than the Sun, exhausts its nuclear fuel, its core collapses catastrophically. The outer layers rebound and explode outward as a supernova, but the core continues collapsing until nuclear forces halt the compression, creating a neutron star about 12 miles across. This neutron star inherits the angular momentum of the original star's core, but because the radius has shrunk by a factor of perhaps 100,000, the rotation rate increases dramatically through conservation of angular momentum. Imagine a figure skater pulling their arms inward during a spin, rotating faster and faster as their radius decreases. The collapsing stellar core undergoes the same process, but on a far more extreme scale. A star that was rotating once every few weeks might produce a neutron star that rotates several times per second. The fastest spinning pulsar known, designated PSRJ 1748-2446 AD, rotates 716 times per second. At its equator, the surface is moving at approximately 70,000 miles per second, nearly 1/4 the speed of light. At these speeds, the neutron star is ablate, bulging significantly at its equator due to centrifugal forces, yet it holds together through the tremendous strength of neutron degenerate matter and its own crushing gravity. The lighthouse effect that makes pulsars detectable comes from their magnetic fields. Neutron stars possess the strongest magnetic fields known in the universe, typically 1 trillion times stronger than Earth's magnetic field. When the core of the parent star collapses, any magnetic field present is compressed and amplified tremendously. This field doesn't simply shrink, it gets concentrated into a much smaller volume, intensifying to values that would tear apart atoms and polarize the vacuum of space itself. This intense magnetic field is not aligned with the neutron star's rotation axis. Just as Earth's magnetic poles don't coincide with its geographic poles, a neutron star's magnetic axis is typically tilted relative to its spin axis. Charged particles, primarily electrons and positrons, are accelerated along the magnetic field lines, particularly near the magnetic poles. These particles, accelerating at relativistic speeds, emit intense beams of radiation through a process called synchrotron radiation. The beams emerge from the magnetic poles, creating 2 searchlights that sweep through space as the neutron star rotates. When one of these beams sweeps across Earth, we detect a pulse of radio waves, X-rays, or gamma rays, depending on the pulsar's characteristics. The pulse arrives with extraordinary regularity. The best pulsars keep time as accurately as atomic clocks, varying by only microseconds over years. This precision exists because the neutron star is such a stable rotator. Its enormous rotational inertia, combined with its extreme density and rigidity, means that nothing can easily change its spin rate. It's like an enormous cosmic flywheel, storing vast amounts of rotational energy and releasing it only very gradually. The radio emission mechanism is complex and still not completely understood, despite decades of study. The acceleration of charged particles near the magnetic poles creates a cascade of electromagnetic radiation. These particles follow the curved magnetic field lines, and as they accelerate, they emit photons. These photons can interact with the intense magnetic field to create more particle-antiparticle pairs, which then accelerate and create more photons, building up a cascade that produces the intense radio emission we detect. The region where this occurs, just above the magnetic poles, is called the polar cap, and it's here that the lighthouse beams originate. Not all pulsars emit at the same wavelengths. Some are primarily radio pulsars, detected through their radio emission. Others are X-ray pulsars, emitting primarily high-energy X-rays. A few emit gamma rays, the most energetic form of electromagnetic radiation. Some pulsars emit across the entire electromagnetic spectrum simultaneously, creating pulses detectable from radio waves through gamma rays. The emission properties depend on factors like the neutron star's age, its magnetic field strength, its rotation rate, and the environment surrounding it. Young pulsars, recently formed in supernova explosions, tend to rotate faster and have stronger magnetic fields than old pulsars. The Crab pulsar, formed in a supernova observed by Chinese astronomers in 1054 AD, rotates 30 times per second and emits powerfully across the electromagnetic spectrum. It sits at the center of the Crab Nebula, the expanding remnant of that supernova explosion, and its intense radiation illuminates the surrounding nebula, causing it to glow. The pulsar acts like a cosmic power station, converting its rotational energy into electromagnetic radiation and high-energy particles that energize the nebula. Pulsars slow down over time, gradually losing rotational energy. This spin-down occurs because the rotating magnetic field acts like a brake. The magnetic field lines extend far into space, and as they rotate with the neutron star, they drag charged particles along, accelerating them and carrying away energy and angular momentum. This magnetic braking gradually robs the neutron star of its rotational energy. A young pulsar might slow down measurably over just a few years, while an old pulsar might take millions of years to show detectable changes in its period. The rate at which a pulsar slows down reveals information about its magnetic field strength and age. By measuring the current rotation period and the rate of change of that period, astronomers can estimate how long the pulsar has been spinning down and how much longer it will continue to pulse before its rotation becomes too slow and its magnetic field too weak to generate detectable radiation. Most pulsars have lifetimes of tens of millions of years as active radio sources before they fade from detectability, though the neutron star itself continues existing and spinning, just no longer producing observable pulses. Some pulsars experience sudden speed-ups, called glitches. The neutron star's rotation rate, which normally decreases steadily, suddenly increases slightly, then resumes its gradual slowdown. These glitches are thought to occur because the neutron star's interior contains a superfluid, a state of matter with zero viscosity that can flow without any resistance. This superfluid rotates faster than the star's crust, and occasionally, angular momentum transfers suddenly from the superfluid to the crust, causing the observable spin-up. Glitches provide rare windows into the exotic physics occurring inside neutron stars, where matter exists in states impossible to recreate in laboratories. Millisecond pulsars present a fascinating puzzle. These pulsars rotate hundreds of times per second, far faster than young pulsars, yet they're old neutron stars, billions of years old. How can an old pulsar be spinning so fast? The answer lies in a process called recycling. A millisecond pulsar was once a normal pulsar that slowed down over hundreds of millions of years. But if it's in a binary system with a companion star, and that companion evolves to become a giant star, matter can flow from the companion onto the neutron star. This infalling matter carries angular momentum, spinning up the neutron star like water hitting a water wheel. Over millions of years, the neutron star is spun up to millisecond periods, recycled into a new youth of rapid rotation. Some pulsars are part of binary systems where we can directly observe this process happening. X-ray binary pulsars show X-ray pulses as the neutron star accretes material from its companion. The infalling material, heated to millions of degrees before hitting the neutron star's surface, emits intense X-rays. These systems are the evolutionary precursors to millisecond pulsars, caught in the act of being spun up by accretion. The most rapidly rotating pulsars ever discovered are all millisecond pulsars, and some of them are in dense globular clusters where stars are packed closely together. The high stellar density in these clusters makes binary interactions more likely, creating environments where many neutron stars can be recycled through accretion. Some globular clusters contain dozens of millisecond pulsars, creating a cosmic percussion section where numerous neutron stars pulse at different rates, each one a precisely ticking clock with its own unique period. Pulsars can also have planets. The first exoplanets ever discovered orbit a pulsar called PSRB 1257+12. These planets were detected through tiny variations in the pulsar's timing. As the planets orbit, their gravity tugs the pulsar slightly back and forth, causing the pulses to arrive slightly early or late in a periodic pattern. The planets orbiting this pulsar are thought to be second-generation worlds, formed from the debris of the supernova explosion that created the neutron star, or possibly from material that later fell back onto the system. These are harsh worlds, bathed in intense radiation from the pulsar, utterly unlike the planets orbiting normal stars. Binary pulsars, where two neutron stars orbit each other, provide extraordinary laboratories for testing general relativity. The orbital motion of such systems produces gravitational waves that carry away energy, causing the orbit to shrink over time. The rate of orbital decay matches Einstein's predictions with incredible precision. The first binary pulsar discovered, PSRB 1913+16, provided the first indirect evidence for gravitational waves, decades before gravitational wave detectors directly observed them from merging black holes and neutron stars. The regularity of pulsar timing has practical applications. Astronomers use networks of millisecond pulsars across the galaxy as a cosmic timing array, watching for tiny correlated deviations in their pulse arrival times that would indicate gravitational waves passing through the galaxy. These pulsar timing arrays are sensitive to gravitational waves with much longer wavelengths than ground-based detectors can observe, potentially detecting the gravitational wave background from supermassive black hole mergers throughout the universe. Pulsars also serve as natural laboratories for extreme physics. The conditions near their surfaces, intense magnetic fields, extreme gravity, densities exceeding that of atomic nuclei, cannot be reproduced on Earth. By observing pulsars across the electromagnetic spectrum and measuring their properties precisely, physicists learn about how matter behaves under conditions that push the boundaries of our physical theories, testing general relativity in strong gravitational fields and probing the equation of state of matter at nuclear densities. These spinning neutron stars, these cosmic lighthouses flashing their beams across the universe, represent one endpoint of stellar evolution. From the violent collapse of a massive star's core emerges an object so dense, so rapidly spinning, so strongly magnetized that it challenges our understanding of physics. Each pulse detected from a pulsar is a message from one of the universe's most extreme environments, a precisely timed signal carrying information about physics at the edge of what's possible, reminding us that the universe contains objects and phenomena far stranger than we could have imagined before we discovered these remarkable, spinning stellar remnants. How we measure the weight of space objects. When astronomers announce that Jupiter has more than 300 times Earth's mass, or that a distant black hole contains several billion times the Sun's mass, these numbers might seem impossibly precise. How can we possibly weigh objects millions or billions of miles away, objects we can never visit or touch, objects that are sometimes completely invisible? The answer lies not in direct measurement, but in observing how these objects interact gravitationally with their surroundings. Mass reveals itself through gravity, and by watching how objects move under gravitational influence, astronomers can calculate masses with remarkable accuracy using principles that Isaac Newton worked out more than 300 years ago. The fundamental principle is simple. The more massive an object is, the stronger its gravitational pull, and the faster other objects must move to orbit it. This relationship, encoded in Newton's law of universal gravitation and his laws of motion, allows us to determine mass from orbital motion. If you know how fast something orbits and how far away it is from the object it's orbiting, you can calculate the central object's mass. For planets in our solar system, we measure their masses by observing their moons. Jupiter has dozens of moons, and each one's orbital period and distance from Jupiter reveals Jupiter's mass. The formula is straightforward in principle. The orbital period squared is proportional to the orbital distance cubed divided by the central mass. By measuring the period and distance, we can solve for the mass. The more massive the central object, the faster moons must orbit at a given distance to avoid falling inward. Jupiter's moon Io orbits very close to Jupiter and completes an orbit in only about 42 hours. Because Jupiter's immense mass creates powerful gravity, our moon takes 27 days to orbit Earth at a similar distance, because Earth is much less massive than Jupiter. For planets without moons, Mercury and Venus, determining mass required more ingenuity. Before the space age, astronomers studied how these planets affected each other's orbits through their gravitational interactions. When two planets pass relatively close to each other, their gravitational pulls slightly deflect each other's paths. By precisely measuring these tiny perturbations over years of observations, astronomers could infer the masses of the planets involved. Space probes visiting these planets provided much more accurate mass measurements by observing how the planet's gravity affected the spacecraft trajectories. Measuring Earth's mass required understanding gravity itself. In the late 18th century, British scientist Henry Cavendish performed a delicate experiment using a torsion balance, a horizontal bar suspended by a thin wire with lead spheres at each end. By bringing large lead masses near the suspended spheres and measuring like the tiny twist in the wire caused by gravitational attraction, Cavendish determined the strength of gravity between known masses. This measurement, combined with the known acceleration of gravity at Earth's surface, allowed calculation of Earth's mass. The experiment is sometimes described as weighing the Earth, though it really measured how strongly Earth's gravity pulls compared to the gravity between laboratory masses. For the Sun, measuring mass is straightforward because Earth and all other planets orbit it. Earth orbits the Sun at a distance of about 150 million kilometers with an orbital period of 1 year. Plugging these numbers into the orbital equation gives the Sun's mass about 2 times 10 to the 30th power kilograms, or about 330,000 times Earth's mass. The exact same calculation works for any star with planets. Measure the planet's orbital distance and period, and you can determine the star's mass. Binary star systems, two stars orbiting each other, provide mass measurements for individual stars. By watching the stars orbit their common center of mass and measuring their orbital periods, distances, and velocities, astronomers can determine both stars' masses separately. This technique has measured thousands of stellar masses, revealing the relationship between a star's mass and its other properties like luminosity and temperature. These measurements show that stars range from about 8% of the Sun's mass for the smallest red dwarfs up to perhaps 150 times the Sun's mass for the most massive stars. For more distant objects, techniques become more sophisticated but still rely on gravitational effects. Galaxies contain hundreds of billions of stars, and measuring a galaxy's mass means measuring how fast stars and gas orbit within it. By observing the rotation speeds at different distances from the galactic center and applying the same orbital principles, astronomers can calculate the total mass enclosed within each radius. This technique revealed the existence of dark matter. The rotation speeds in the outer parts of galaxies are far too high to be explained by the visible stars and gas alone, requiring the presence of large amounts of invisible mass. Galaxy clusters, groups of hundreds or thousands of galaxies, have their masses measured through multiple techniques. One method observes the motions of individual galaxies within the cluster. The galaxies orbit within the cluster's gravitational potential, and their velocities reveal the cluster's total mass. Another technique uses gravitational lensing, the bending of light from more distant galaxies by the cluster's gravity. The amount of bending depends on the cluster's mass, so by measuring how background galaxies appear distorted, astronomers can map the cluster's mass distribution, including dark matter. Black holes present special challenges because they are invisible and often have no nearby objects in simple orbits. For stellar mass black holes in binary systems, astronomers measure the orbital motion of the visible companion star. The star's velocity and orbital period reveal the black hole's mass, even though the black hole itself emits no light. This technique confirmed that several X-ray binary systems contain objects too massive to be neutron stars. They must be black holes. Supermassive black holes at galaxy centers are weighed by observing stars or gas orbiting near them. The Milky Way's central black hole, Sagittarius A star, has its mass measured precisely by tracking individual stars as they orbit. One star, designated S2, completes an orbit every 16 years in an elongated ellipse that brings it within about 120 times Earth's distance from the Sun, extremely close by galactic standards. By measuring S2's position and velocity throughout its orbit, astronomers calculated the black hole's mass at about 4 million times the Sun's mass. This measurement is accurate to within a few percent, despite the black hole being 26,000 light-years away. More distant supermassive black holes are measured through the motion of stars or gas closer to the black hole than telescopes can individually resolve. Instead, spectroscopy measures the range of velocities present in the light coming from the galaxy's central region. Broader velocity distributions indicate faster-moving material, which requires more mass to keep the material bound. Using this technique, astronomers have measured black hole masses ranging from millions to billions of solar masses in galaxies across the universe. Gravitational waves from merging black holes provide another mass measurement technique. When two black holes spiral together and merge, they emit gravitational waves, ripples in space-time itself, detected by observatories like LIGO. The frequency and amplitude of these waves encode information about the black hole's masses. The first gravitational wave detection in 2015 came from two black holes weighing about 29 and 36 solar masses that merged into a single black hole of about 62 solar masses. with 3 solar masses worth of energy radiated away as gravitational waves during the collision. For objects we can visit with spacecraft, mass measurements become more direct. The spacecraft's trajectory bends as it passes the object, with the deflection determined by the object's mass. By tracking the spacecraft's position using radio signals and measuring the Doppler shift in those signals, mission controllers determine the trajectory precisely. Comparing the observed trajectory to computer models reveals the mass that must have caused that particular deflection. This technique has measured masses of asteroids, comets, and moons with no satellites of their own. Small asteroids present particular challenges. Without satellites, and too small to significantly affect spacecraft at typical flyby distances, their masses remained uncertain until spacecraft flew very close or even orbited them. The near-Shoemaker spacecraft orbited asteroid Eros for a year, precisely measuring Eros's mass and density. The Hayabusa and OSIRIS-REx missions orbited small asteroids, Ryugu and Bennu respectively, measuring their masses through orbital mechanics and revealing that both asteroids are loose rubble piles rather than solid rocks. The precision of mass measurements varies enormously. The Sun's mass is known to about 7 significant figures. Earth's mass is known even more precisely because we can measure Earth's gravitational field from satellites in low orbit. Jupiter's mass is known very precisely from spacecraft tracking, but the mass of a distant galaxy might be uncertain by 10 or 20%, and masses of galaxy clusters can be uncertain by even more, particularly if dark matter doesn't follow the same distribution as visible matter. Understanding the limitations matters. When astronomers quote a mass, there's always uncertainty attached. Reporting that a black hole contains about 4 million solar masses acknowledges this uncertainty. The actual value might be 3.8 million or 4.2 million, and that range represents our measurement precision, not variability in the black hole's mass. All these techniques ultimately trace back to gravity, the fundamental force that governs how massive objects interact across space. Mass creates gravity, gravity creates motion, and by observing that motion precisely, we can work backward to determine the mass that caused it. From moons orbiting planets, to galaxies orbiting within clusters, from binary stars wheeling around each other, to stars orbiting supermassive black holes, the cosmos is filled with objects whose motions reveal the masses of the bodies that control them. By watching these cosmic dances and applying the mathematical laws that Newton first articulated, astronomers can weigh objects from the smallest asteroids to the largest galaxy clusters, measuring masses across a range spanning more than 20 orders of magnitude. From asteroids weighing billions of tons to galaxy clusters weighing millions of trillions of times more than the Sun, all without ever placing these objects on a scale, relying instead on the universal language of gravity that connects everything in the cosmos through the elegant mathematics of orbital motion. The cosmic web that connects galaxies. When you look up at the night sky, the stars appear scattered across the darkness in what seems like a random pattern. Galaxies, those island universes containing billions of stars, seem to float in isolation, separated by vast gulfs of empty space. But zoom out far enough, pull back your perspective to encompass not just our galaxy or our local group of galaxies, but thousands, then millions, then billions of galaxies, and an extraordinary pattern emerges. The universe is not random at all. It's organized into a structure so vast and intricate that it resembles a three-dimensional spider's web stretching across the entire observable cosmos. This structure, called the cosmic web, represents the largest known organizational pattern in the universe. Picture it in your mind. Long filaments of galaxies stretching across hundreds of millions of light years, connecting at massive nodes where galaxy clusters gather. Between these filaments lie enormous voids, regions of space so empty that they contain almost no galaxies at all. The filaments themselves are like highways of matter, channels along which gas flows and galaxies form, creating luminous threads that trace out the underlying architecture of space itself. The story of the cosmic web begins in the earliest moments after the Big Bang. In those first fractions of a second, the universe was nearly uniform, filled with hot plasma that was almost, but not quite, perfectly smooth. Tiny quantum fluctuations, variations in density that were only 1 part in 100,000, existed throughout this primordial material. These minuscule differences seemed insignificant, but they contained the seeds of everything that would come after. As the universe expanded and cooled, gravity began to amplify these tiny variations. Regions that were even slightly denser than average had slightly stronger gravity, which pulled in surrounding matter, making them denser still. This process fed on itself, with denser regions becoming denser over time, while less dense regions became emptier as their matter drained away toward the dense areas. But matter didn't just collapse into points, it collapsed along preferred directions, following the geometry dictated by the initial distribution of fluctuations. Imagine pouring cream into coffee and watching it swirl and fold into complex patterns before mixing completely. The early universe underwent something similar, but instead of mixing, the patterns froze into place, held there by gravity. Matter flowed along the paths of least resistance, streaming toward concentrations of mass, creating sheets and filaments rather than distributing itself uniformly. Dark matter played a crucial role in creating this web. This mysterious substance, which doesn't emit or absorb light but exerts gravitational force, makes up about 85% of all matter in the universe. Dark matter began clustering earlier than normal matter because it doesn't interact with light or other radiation. It formed a gravitational scaffolding, a framework of invisible mass and normal matter. The hydrogen and helium gas that would eventually form stars and galaxies fell into the gravitational wells created by this dark matter framework. The filaments of the cosmic web are not thin lines, but rather thick structures, typically about 20 to 30 million light-years across, and stretching for hundreds of millions of light-years in length. Along these filaments, galaxies form like beads on a string, though the string itself is made of dark matter with tendrils of gas threading through it. The gas in these filaments exists in a warm to hot state, typically between 100,000 and 10 million degrees, hot enough that it emits X-rays, but not dense enough to be easily observable. At the intersections where multiple filaments meet, enormous galaxy clusters form. These are the cities of the cosmic web, containing hundreds or even thousands of galaxies bound together by gravity. The largest galaxy clusters can contain as much mass as 1,000,000 billion suns, most of it in the form of dark matter, with substantial amounts of hot gas filling the space between galaxies. These clusters mark the nodes of the web, the places where matter has concentrated most densely. Between the filaments lie the cosmic voids, vast regions of space that are remarkably empty. A typical void might be 150 million light-years across and contain very few galaxies. These aren't completely empty. They still contain dark matter and some diffuse gas, but their density is only about 10 to 20% of the average density of the universe. Voids expand over time as matter continues to flow out of them toward the filaments and clusters, making them emptier with each passing billion years. The cosmic web reveals itself to astronomers through large-scale galaxy surveys. Telescopes map the positions of millions of galaxies, measuring not just where they appear in the sky, but also how far away they are. This three-dimensional mapping shows the web's structure clearly. Some of the most famous structures include the Sloan Great Wall, a concentration of galaxies stretching across 1.4 billion light-years, and the Hercules Corona Borealis Great Wall, which spans an almost incomprehensible 10 billion light-years. Our own Milky Way galaxy sits within this web, part of what's called the local group, a small collection of about 50 galaxies, including the Andromeda Galaxy and various smaller dwarf galaxies. This local group is located on the outskirts of the Virgo supercluster, a massive structure containing thousands of galaxies. Recent mapping has revealed that the Virgo supercluster is itself part of an even larger structure called Laniakea, a supercluster of superclusters spanning 520 million light-years and containing the mass of about 100,000 trillion suns. The gas flowing through the cosmic web carries matter from the voids into the filaments, and from the filaments into the galaxy clusters. This flow is not gentle. Gas moving through the filaments can reach speeds of several hundred kilometers per second, and when streams of gas collide at cluster locations, shock waves heat the gas to tremendous temperatures. These shock waves, called accretion shocks, occur at the boundaries of clusters where the web feeds new material into these gravitationally bound systems. Galaxies forming within the filaments have different characteristics than galaxies forming in the voids or clusters. Filament galaxies have better access to the gas supply flowing through the web, which allows them to continue forming stars for longer periods. Cluster galaxies, surrounded by hot gas and interacting frequently with other galaxies, often exhaust their star-forming fuel more quickly. Void galaxies, isolated and with limited gas supply, tend to be smaller and less luminous. The web is not static. It evolves over cosmic time as gravity continues to pull matter along its channels. Computer simulations of the universe's evolution show that the web was less pronounced in the early universe and has become more defined over billions of years. The voids have expanded. The filaments have thinned in some places while becoming more pronounced in others, and the galaxy clusters have grown larger as they consume matter from the surrounding web. Dark energy complicates this picture. This mysterious force which causes the universe's expansion to accelerate works against gravity's tendency to pull matter together. While gravity tries to make the web more concentrated, dark energy pushes space apart. The current era represents a transition. For the first several billion years after the Big Bang, gravity dominated and the web continued to grow more structured. But as dark energy's influence has grown stronger over time, it has begun to limit further structure growth. In the far future, dark energy will win, pulling the filaments apart and eventually isolating each galaxy cluster as an island in an ever-expanding sea of space. Scientists study the cosmic web using multiple techniques. Optical telescopes map the positions of galaxies. Radio telescopes detect the neutral hydrogen gas in and around galaxies. X-ray telescopes observe the hot gas in galaxy clusters and filaments. By combining these different views, astronomers build up a comprehensive picture of where matter exists and how it moves through the web's structure. The web also serves as a cosmic laboratory for studying dark matter. The way galaxies move within filaments and clusters, and the bending of light from distant objects as it passes through the web's mass concentrations, both provide information about the distribution of dark matter. These observations have helped confirm that dark matter exists, and have constrained theories about what dark matter might be, even though its fundamental nature remains one of physics' deepest mysteries. On the very largest scales, the cosmic web shows a surprising degree of uniformity. While the web has complex structure on scales up to a few 100 million light-years, if you average over regions a billion light-years or larger, the universe looks remarkably similar in all directions. This homogeneity on the largest scales supports the cosmological principle, the idea that on sufficiently large scales, the universe is essentially the same everywhere, with no preferred locations or directions. The web continues to influence galaxy evolution today. Our own galaxy, the Milky Way, is being pulled through space by the gravitational attraction of the web's structure. We're falling toward the Virgo cluster at about 400 kilometers per second, and at the same time, our entire local supercluster is being pulled toward an even more massive concentration of galaxies in the direction of the constellations Centaurus and Hydra, a region astronomers call the Great Attractor. Understanding the cosmic web means understanding how the universe transformed from a nearly smooth state shortly after the Big Bang into the rich, structured cosmos we see today. The web is a fossil record of the universe's history, preserving information about the initial conditions that existed billions of years ago, and documenting the ongoing battle between gravity, trying to pull matter together, and cosmic expansion, trying to spread it apart. Every galaxy in the night sky exists where it does because of this vast structure, this intricate architecture that connects everything in the universe into one enormous, evolving pattern. The afterglow of the Big Bang. Throughout the entire universe, in every direction you could possibly look, there exists a faint glow of microwave radiation that fills all of space. This radiation isn't coming from stars or galaxies or any object in particular. It's coming from everywhere at once, a ghostly remnant from the earliest moments of cosmic history. This is the cosmic microwave background, the oldest light in the universe, and it carries within it a snapshot of what the cosmos looked like when it was just 380,000 years old, a mere infant compared to its current age of 13.8 billion years. To understand this afterglow, picture the universe in its earliest moments. At the very beginning, everything that exists now, all the matter and energy in hundreds of billions of galaxies, was compressed into an infinitesimally small point. The Big Bang wasn't an explosion in space, but rather an expansion of space itself. In those first fractions of a second, the universe was unimaginably hot and dense, so hot that matter as we know it couldn't exist. There were no atoms, no nuclei, not even stable protons or neutrons. There was only a seething soup of fundamental particles and energy, all in thermal equilibrium at temperatures of trillions upon trillions of degrees. As the universe expanded, it cooled, following a fundamental principle of thermodynamics. Think of how a spray can get cold when you release the compressed gas inside. Expansion causes cooling. The universe cooled rapidly in those early moments, dropping from inconceivable temperatures down to merely billions of degrees within the first few minutes. At this point, conditions became cool enough for protons and neutrons to stick together, forming the nuclei of the lightest elements, primarily hydrogen, some helium, and trace amounts of lithium and beryllium. This period, called Big Bang nucleosynthesis, lasted only about 17 minutes, but it determined the basic chemical composition of the universe for hundreds of millions of years to come. But even after nuclei formed, the universe was still far too hot for atoms to exist. Free electrons zipped through space at tremendous velocities, and any time they got near a nucleus, the ambient heat would knock them away before they could settle into orbit. The universe was filled with a plasma, a mixture of atomic nuclei and free electrons, and this plasma was opaque to light. Photons couldn't travel far before colliding with a free electron and scattering in a new direction. Light was trapped, bouncing endlessly between particles in a cosmic fog that filled all of space. For the next 380,000 years, the universe continued expanding and cooling, but it remained opaque. The temperature dropped gradually, from millions of degrees down to thousands of degrees. Then at around 3,000 degrees Kelvin, still hot enough to melt any metal, something remarkable happened. The universe had finally cooled enough for electrons to combine with nuclei and form stable atoms. This moment is called recombination, though that's actually a misnomer since the electrons and nuclei were combining for the first time, not recombining. When recombination occurred, the nature of the universe changed fundamentally. With electrons now bound into atoms, there were suddenly far fewer free charged particles for photons to scatter off of. The cosmic fog cleared almost instantaneously on cosmic timescales. Light that had been trapped, scattering endlessly through the plasma, was suddenly free to travel unimpeded through space. the universe became transparent. The photons that were released at that moment of recombination have been traveling through space ever since. They filled the entire universe then, and they fill the entire universe now. These photons form the cosmic microwave background. They are the afterglow of the Big Bang, the first light that could freely travel through the cosmos. But here's the crucial part. Those photons have been stretched by the expansion of the universe. When they were released 13.8 billion years ago, they were primarily visible light and infrared radiation, corresponding to the 3000-degree temperature of the universe at recombination. But as space itself expanded, the wavelengths of these photons were stretched along with it. Light that was once visible orange has been stretched into infrared, then into far infrared, and finally into microwave radiation. The cosmic microwave background today corresponds to a temperature of just 2.7 degrees above absolute zero, 2.7 Kelvin. This stretching of light by the expansion of space is called cosmological redshift, and it's one of the most direct pieces of evidence for the Big Bang theory. The universe has expanded by a factor of about 1,100 since recombination, and the wavelength of the cosmic microwave background radiation has been stretched by exactly this same factor. What was once a hot glow of visible light has become a cold bath of microwave radiation. The cosmic microwave background is incredibly uniform. No matter which direction you look in the sky, the temperature is almost exactly the same, 2.725 Kelvin, with variations of only about 1 part in 100,000. This uniformity tells us that the early universe was remarkably smooth and homogeneous. There were no large structures, no concentrations of matter, just an almost perfectly uniform distribution of hydrogen and helium gas filling all of space. But those tiny variations, those fluctuations of 1 part in 100,000, are extraordinarily important. They represent slight differences in density and temperature in the primordial plasma. Some regions were slightly denser and hotter, others slightly less dense and cooler. These fluctuations were the seeds of all structure in the universe today. The denser regions had slightly stronger gravity, which allowed them to attract more matter over time. Over hundreds of millions of years, these tiny density differences grew, eventually collapsing to form the first stars, then galaxies, then galaxy clusters, and ultimately the entire cosmic web of structure we see today. When astronomers map the cosmic microwave background in detail, they're seeing a snapshot of these primordial fluctuations. Sophisticated satellites, equipped with incredibly sensitive detectors, measure the temperature of the cosmic microwave background across the entire sky, creating maps that show warmer and cooler spots. These maps look like mottled patterns of slightly different colours, almost like abstract art, but they're actually baby pictures of the universe, showing the distribution of matter when the cosmos was just 380,000 years old. The patterns in the cosmic microwave background aren't random. They have specific statistical properties that depend on the fundamental parameters of the universe. How much normal matter exists, how much dark matter, how much dark energy, the rate of expansion, the curvature of space, and more. By analysing these patterns in exquisite detail, cosmologists can measure these parameters with remarkable precision. The cosmic microwave background has become the single most important tool for determining the basic properties of our universe. One of the most striking features visible in cosmic microwave background maps is the presence of acoustic oscillations, essentially sound waves in the primordial plasma. Before recombination, the plasma was hot and under tremendous pressure from radiation. Regions that were slightly denser had stronger gravity pulling inward, but they also had stronger radiation pressure pushing outward. These competing forces created oscillations, with dense regions compressing and then rebounding, creating waves that propagated through the plasma, much like sound waves travel through air. These acoustic oscillations were frozen into the distribution of matter at the moment of recombination. The characteristic scale of these oscillations, the typical distance between peaks and troughs, shows up as a specific pattern in the cosmic microwave background, radiation background, temperature fluctuations. By measuring this pattern precisely, astronomers can determine how far these sound waves had travelled by the time of recombination, which in turn tells them about the geometry and expansion rate of the universe. The cosmic microwave background also has a subtle property called polarization. Light can be polarized, its electric field can oscillate in a preferred direction, and the cosmic microwave background photons carry polarization information from the moment they were released. This polarization was created when the photons scattered off electrons for the last time before recombination. The pattern of polarization across the sky carries additional information about conditions in the early universe, including potentially evidence of gravitational waves from the inflationary period that may have occurred in the first tiny fraction of a second after the Big Bang. There are actually two types of polarization patterns in the cosmic microwave background, called E modes and B modes. E modes are relatively easy to detect and have been thoroughly mapped. B modes are much fainter and harder to detect, but they're particularly interesting because primordial gravitational waves would create a specific B mode pattern. Detecting this signal would provide direct evidence for cosmic inflation and would open a window into physics at energy scales far beyond what we can achieve in particle accelerators on Earth. The cosmic microwave background isn't perfectly smooth in its distribution across the sky. There's a slight asymmetry, a dipole pattern, where one side of the sky is slightly hotter and the other slightly cooler. This dipole is caused by the motion of our solar system through space. We're moving at about 370 kilometers per second relative to the cosmic microwave background, carried along by the motion of the Sun around the galaxy, the motion of the galaxy through the local group, and the motion of the local group through the universe. This motion causes the cosmic microwave background to appear slightly blue-shifted, and therefore hotter in the direction we're moving toward, and slightly red-shifted, and cooler in the direction we're moving away from. Once this dipole is removed from the data, along with contamination from our own galaxy's emission, what remains are the primordial fluctuations, the image of the universe as it was 380,000 years after the Big Bang. These fluctuations exist on multiple scales, from features spanning large portions of the sky down to the smallest angular scales that satellites can resolve. Each scale carries different information about the early universe and the physical processes that shaped it. The cosmic microwave background has also been used to test fundamental physics. The spectrum of the radiation, how much energy exists at each wavelength, matches a perfect blackbody spectrum, more precisely than any artificial source humans have ever created. This perfect blackbody spectrum is exactly what's expected from matter and radiation in perfect thermal equilibrium, providing strong confirmation that the early universe was indeed in this state. Photons from the cosmic microwave background pass through everything. Right now, billions of these ancient photons are streaming through your body every second, traveling through space for nearly 14 billion years before encountering the atoms in your cells. They pass through largely without interaction because microwave radiation interacts very weakly with ordinary matter at everyday temperatures. The entire Earth is bathed in this ancient light, as is every planet, every star, every galaxy. It's a universal background that permeates all of existence. The discovery of the cosmic microwave background in 1964 was accidental. Two radio astronomers, Arno Penzias and Robert Wilson, were testing a sensitive radio antenna and kept detecting a persistent noise that came from all directions and wouldn't go away no matter what they did. They initially thought it might be interference from nearby New York City, or perhaps noise from the electronics, or even from bird droppings on the antenna. Only when they consulted with theoretical physicists did they realize they had detected the afterglow of the Big Bang, earning them the Nobel Prize. This radiation has been cooling for billions of years and will continue cooling forever. As the universe expands, the cosmic microwave background will be stretched to longer and longer wavelengths, eventually becoming radio waves, then longer wavelengths still. Its temperature will approach closer and closer to absolute zero, but will never quite reach it, always remaining as a faint reminder of the hot, dense state from which our universe emerged, carrying information about cosmic dawn across the vastness of space and time. The chemistry required for life beyond Earth. Life at its most fundamental level is chemistry. Every thought you think, every breath you take, every movement you make results from chemical reactions occurring in your cells. Molecules bind together and break apart. Energy flows from one form to another. And through countless chemical transformations, inanimate matter becomes animate. Dead molecules become living organisms. Understanding what chemistry is required for life beyond Earth means understanding what makes life possible at all. The elements, the reactions, the solvents, and the energy sources that could allow chemistry to cross the threshold from complex but lifeless reactions into something that grows, reproduces, evolves, and ultimately builds civilizations among the stars. Carbon stands at the center of all known life. Every organism on Earth, from bacteria to blue whales, builds its body from carbon-based molecules. Carbon's unique properties make it extraordinarily suitable for life. Each carbon atom can form 4 chemical bonds with other atoms, allowing it to create an immense diversity of molecular structures, long chains, branching trees, rings, and complex 3-dimensional shapes. Carbon bonds with itself strongly enough to create stable molecules, but not so strongly that the bonds cannot be broken and rearranged through normal chemical reactions. This balance allows carbon molecules to be both stable enough to maintain structure and reactive enough to participate in the constant chemical transformations that life requires. Organic chemistry, the chemistry of carbon compounds, encompasses millions of known molecules and potentially billions more that could exist. Carbon combines readily with hydrogen, oxygen, nitrogen, sulfur, and phosphorus to create the molecules of life. Proteins, the workhorses of cells that catalyze reactions and build structures, are chains of amino acids linked together, each amino acid containing carbon, hydrogen, oxygen, and nitrogen. DNA and RNA, which store and transmit genetic information, are built from carbon-containing sugars, phosphate groups, and nitrogen-rich bases. Lipids, which form cell membranes and store energy, are long carbon chains with various functional groups attached. Carbohydrates, which provide energy and structural support, are carbon molecules with hydrogen and oxygen in specific ratios. But is carbon truly necessary for life, or is it simply the element that happened to work on Earth? Silicon, sitting directly below carbon in the periodic table, shares many of carbon's properties. Silicon also forms 4 chemical bonds and can create chains and rings similar to carbon. Science fiction has long speculated about silicon-based life, but silicon faces significant challenges. Silicon-silicon bonds are weaker than carbon-carbon bonds, making long silicon chains less stable. Silicon compounds tend to be much less diverse than carbon compounds. While carbon forms millions of different molecules, silicon chemistry is far more limited. Most critically, silicon's most common compound is silicon dioxide, quartz, sand, rock, which is extremely stable and insoluble. When silicon burns with oxygen, it creates solid rock rather than a gas that can be easily expelled and recycled. However, silicon-based life might be possible in environments completely unlike Earth. In extremely cold environments where water is frozen solid, silicon chemistry might become more favorable. In the presence of liquid hydrocarbons instead of water, silicon compounds might behave differently, remaining soluble and reactive rather than precipitating as rocks. A frigid world with seas of liquid methane or ethane, like Saturn's moon Titan, might provide conditions where silicon-based biochemistry could operate. Such life would function on completely different principles than Earth's carbon-based organisms, but it might still meet the basic requirements: complexity, self-replication, evolution, and metabolism. Hydrogen plays a crucial role in biochemistry beyond being part of organic molecules. Hydrogen ions, protons, are essential for energy generation in cells. Earth's organisms create differences in hydrogen ion concentration across membranes, then allow the ions to flow back through specialized proteins called ATP synthase, which harness the flowing ions to create ATP, the universal energy currency of life. This process, called chemiosmosis, powers nearly all life on Earth and represents a fundamental way of coupling energy sources to useful work. Any biochemistry, whether carbon-based or otherwise, would need some mechanism for capturing and storing energy, and hydrogen's simple chemistry makes it an excellent candidate for this role, regardless of the specific biochemistry involved. Oxygen serves multiple roles in Earth's biochemistry. It's part of water, part of most organic molecules, and it serves as the final electron acceptor in cellular respiration, the process by which organisms extract energy from food. When glucose is metabolized with oxygen, the reaction releases large amounts of energy that cells capture in the chemical bonds of ATP. This oxygen-based metabolism, called aerobic respiration, is far more efficient than metabolism without oxygen. However, oxygen was not always available on Earth. For the first 2 billion years or more, Earth's atmosphere contained very little free oxygen, and early life functioned without it, using anaerobic metabolism based on different chemical reactions. Some organisms today still live without oxygen, in deep ocean sediments or the guts of animals, using sulfur compounds, nitrates, or iron as alternatives to oxygen. Life beyond Earth might never develop oxygen-based metabolism if oxygen never becomes abundant in the atmosphere. Planets orbiting red dwarf stars might have difficulty accumulating oxygen because ultraviolet light from the star, which on Earth helps break apart water molecules in the upper atmosphere, leading to oxygen accumulation, is less intense. Life on such worlds might remain dependent on anaerobic metabolism indefinitely, which would likely limit the size and energy consumption of organisms. Active, energy-intensive lifestyles, like those of birds or mammals, require the high energy output that only oxygen metabolism provides. Alien life using alternative metabolic pathways might be restricted to smaller, slower, lower energy forms. Nitrogen is essential for proteins and nucleic acids. It's found in amino acids and in the bases that make up DNA and RNA. Nitrogen chemistry is complex and often difficult. Nitrogen gas in the atmosphere consists of 2 nitrogen atoms triple bonded together, making it very stable and unreactive. Converting atmospheric nitrogen into biologically useful forms, a process called nitrogen fixation, requires significant energy or specialized catalysts. On Earth, certain bacteria can fix nitrogen using enzymes containing iron and molybdenum. Lightning also fixes nitrogen by forcing nitrogen and oxygen to react in the high energy conditions of electrical discharge. Life on other planets would need some source of biologically available nitrogen, either through similar fixation processes or through nitrogen already present in reactive forms. Phosphorus plays a unique and critical role in biochemistry. It's part of the backbone of DNA and RNA, linking the sugar molecules together into the long chains that store genetic information. It's also central to ATP, the molecule that stores and transfers energy in cells. Phosphate groups can be added to and removed from molecules to regulate their activity, serving as switches that turn cellular processes on and off. There is no obvious substitute for phosphorus in these roles. Unlike carbon, nitrogen, and oxygen, which are abundant in the universe, Phosphorus is relatively rare, created only in certain types of stellar processes. A planet poor in phosphorus might struggle to develop complex life, at least of the kind we would recognize. Sulfur contributes to protein structure through disulfide bonds, connections between sulfur atoms in different parts of a protein that help the protein fold into its proper three-dimensional shape. Some organisms use sulfur compounds in their metabolism instead of or in addition to oxygen. Near hydrothermal vents on Earth's ocean floor, bacteria oxidize hydrogen sulfide, the compound that smells like rotten eggs, to generate energy. Entire ecosystems build on these chemosynthetic bacteria, demonstrating that sunlight and photosynthesis are not necessary for life. An alien world with extensive volcanic or hydrothermal activity could support life based on sulfur chemistry, even in complete darkness. Trace elements, though needed in tiny amounts, are essential for many biological processes. Iron is central to hemoglobin, the protein that carries oxygen in blood, and to many enzymes involved in energy metabolism. Magnesium sits at the center of chlorophyll molecules, enabling photosynthesis. Zinc, copper, manganese, and other metals serve as cofactors for enzymes, helping catalyze reactions that would otherwise proceed too slowly to sustain life. An alien biochemistry would likely require its own set of trace elements, perhaps using metals common on its world but rare on Earth, or finding entirely different solutions to catalysis and molecular structure. Water serves as the solvent for biochemistry on Earth, the medium in which all cellular chemistry occurs. Water has remarkable properties that make it ideal for life. It remains liquid across a wide temperature range, from 0 to 100 degrees Celsius at Earth's atmospheric pressure. It has a high heat capacity, meaning it resists temperature changes, which helps organisms maintain stable internal temperatures. Water molecules are polar, with a slight positive charge on one end and a slight negative charge on the other, allowing water to dissolve ionic compounds and interact with many different types of molecules. The hydrogen bonds between water molecules create surface tension, capillary action, and the unusual property that ice floats on liquid water, a characteristic that has profound implications for life in oceans and lakes. But is water necessary for life? Or might other liquids serve as solvents for alternative biochemistries? Ammonia has been proposed as a possible alternative. Ammonia remains liquid at much colder temperatures than water. It freezes at -78 degrees Celsius and boils at -33 degrees Celsius at Earth's atmospheric pressure. A very cold planet, too cold for liquid water, might have lakes or oceans of liquid ammonia. Ammonia shares some of water's properties. It's polar, can form hydrogen bonds, and dissolves many substances. However, ammonia is a less effective solvent than water for many compounds, and the biochemistry that could operate in liquid ammonia would necessarily be very different from Earth's water-based life. Methane and ethane, though non-polar and very different from water, exist as liquids on Titan, Saturn's largest moon. Titan has lakes and rivers of liquid hydrocarbons on its surface, creating a hydrological cycle remarkably similar to Earth's water cycle, but operating at temperatures around -180 degrees Celsius. Could life exist in these hydrocarbon lakes? The chemistry would be completely unlike anything on Earth. Reactions that occur readily in water might not occur at all in methane, while entirely different reactions become possible. Cell membranes would need to be built from different molecules. The lipid membranes used by Earth's cells wouldn't function in liquid methane. Energy metabolism would follow different pathways. But some scientists argue that the sheer strangeness of Titan's environment doesn't preclude life, only life that operates on unfamiliar principles. Supercritical fluids represent another possibility. Under high pressure and high temperature, substances enter a supercritical state where the distinction between liquid and gas breaks down. Supercritical carbon dioxide, for instance, behaves as both liquid and gas simultaneously, with properties of each. Deep beneath the surfaces of certain planets, conditions might create supercritical water or other supercritical fluids that could potentially serve as solvents for exotic biochemistries operating under extreme conditions. Energy sources drive all biochemistry. On Earth, sunlight powers most ecosystems through photosynthesis. Plants and photosynthetic bacteria capture light energy and use it to build organic molecules from carbon dioxide and water. These organic molecules then flow through food chains, ultimately providing energy for all other organisms. But many alternative energy sources exist. Chemical energy from redox reactions, where electrons transfer from one molecule to another, can sustain life in complete darkness. Radioactive decay in a planet's interior could provide steady energy through the heat it generates, potentially supporting life in subsurface environments for billions of years, even if the star above has long since died. The origin of life, the transition from complex chemistry to living organisms, requires conditions where organic molecules can form, concentrate, and begin the process of self-replication and evolution. On Earth, this might have occurred in tidal pools, in hydrothermal vents, in ice, or even in the atmosphere. The exact location and mechanism remain uncertain, but the chemistry required involves forming increasingly complex molecules from simpler precursors, eventually creating molecules capable of catalyzing reactions, including their own replication. This requires an energy source to drive uphill reactions that create complexity from simplicity, fighting against entropy. It requires some form of containment, membranes or surfaces, to concentrate molecules and create distinct chemical environments. And it requires time for random chemical processes to explore countless possibilities until self-replicating systems emerge. The universality of certain chemical principles suggests that life elsewhere, no matter how alien, would still obey the same rules of chemistry and thermodynamics that govern Earth's life. All life must extract energy from its environment and use that energy to create and maintain complex organization. All life must reproduce, passing information to offspring. All life must evolve through variation and selection. These requirements constrain the chemistry of life, regardless of what specific molecules are involved. Carbon is not the only possible basis for complex chemistry, water is not the only possible solvent, and oxygen is not the only possible energy source, but any living system must solve the same fundamental chemical problems: how to capture and store energy, how to build complex molecules, how to replicate information, and how to maintain organization in a universe that constantly tends toward disorder. The chemistry required for life beyond Earth encompasses the familiar carbon, water, proteins, and DNA, and the exotic silicon biochemistry in hydrocarbon seas, life in supercritical fluids, using metals we've never heard of, organisms metabolizing on reactions we've never imagined. The universe provides the raw materials everywhere: hydrogen from the Big Bang, heavier elements forged in stars and scattered through supernova explosions. Every planet, moon, and asteroid contains chemistry, happening constantly through radiation, temperature gradients, and the simple mixing of different compounds. Whether that chemistry crosses the threshold into life depends on having the right combination of elements, solvents, energy sources, and time, ingredients that might exist on countless worlds throughout the cosmos, waiting for chemistry to become biology in endless variations on the theme of life. The extreme environments where life could thrive. Life on Earth exists in places that seem utterly hostile to survival: in boiling hot springs where water approaches its boiling point, in frozen Antarctic lakes where temperatures remain below zero year-round, in crushing depths of the ocean where pressure would flatten most organisms instantly, in intensely acidic pools that would dissolve metal, and in radioactive waste sites where radiation levels would kill a human in hours. These extreme environments, once thought to be sterile and lifeless, actually teem with organisms called extremophiles, life forms that not only survive but thrive in conditions that would destroy most familiar creatures. Understanding where these extremophiles live and how they manage to exist in such harsh conditions reveals that life's possibilities extend far beyond the comfortable, temperate zones we associate with habitability, suggesting that alien life might flourish in environments throughout the universe that we would never have considered searching. Temperature extremes represent one of the most dramatic challenges for life. At Yellowstone National Park and similar geothermal areas worldwide, hot springs reach temperatures near or even above the boiling point of water. In these scalding pools, organisms called thermophiles and hyperthermophiles thrive at temperatures that would cook most life forms. Some bacteria live comfortably at temperatures around 180 degrees Fahrenheit, and certain archaea, single-celled organisms distinct from bacteria, can survive and reproduce at temperatures exceeding 230 degrees Fahrenheit in superheated water under pressure that prevents it from boiling. These heat-loving organisms have specialized proteins that maintain their structure at high temperatures instead of denaturing and unfolding like normal proteins would. Their cell membranes contain special lipids that remain fluid and functional at temperatures where ordinary membranes would fall apart. Their DNA includes protective mechanisms that prevent the double helix from separating under thermal stress. Every aspect of their biochemistry has been optimized through evolution to function at temperatures that would destroy conventional life in seconds. The existence of thermophiles suggests that life could exist in hot environments throughout the solar system and beyond. In volcanic hot springs on Mars, in heated cracks near lava flows on Jupiter's moon Io, or in the scalding oceans of planets closer to their stars than Earth is to the Sun. At the opposite extreme, psychrophiles, cold-loving organisms, thrive at temperatures well below the freezing point of pure water. In Antarctica, microbes live in lakes that remain liquid beneath ice, because salt lowers the freezing point, maintaining temperatures around -5 to -20 degrees Fahrenheit. These organisms produce antifreeze proteins that prevent ice crystals from forming inside their cells, manufacture enzymes that remain flexible and functional at temperatures where normal enzymes become rigid and useless, and slow their metabolisms to conserve energy in the cold. Some bacteria found in permafrost remain viable after being frozen for hundreds of thousands of years, suggesting remarkable cold tolerance. The discovery of psychrophiles revolutionized thinking about where life could exist in the solar system. Europa, Jupiter's ice-covered moon, has a liquid ocean beneath miles of surface ice, kept liquid by tidal heating from Jupiter's gravity. The water at the bottom of this ocean, near Europa's rocky core, might be relatively warm, perhaps just above freezing, and could host psychrophilic life adapted to darkness and cold. Enceladus, Saturn's small moon, shoots geysers of liquid water through cracks in its ice shell, water that comes from a subsurface ocean. Despite the frigid surface temperature of -330 degrees Fahrenheit, the ocean beneath remains liquid, warmed by tidal forces. Life in these hidden oceans would need to tolerate extreme cold, total darkness, and high pressure, but Earth's psychrophiles prove that temperature alone doesn't preclude life. Pressure creates another extreme that life has conquered remarkably. In the Mariana Trench, the deepest part of Earth's oceans, pressure reaches about 16,000 pounds per square inch, more than 1,000 times atmospheric pressure at sea level. This crushing pressure would compress gases, alter protein structures, and collapse air-filled spaces in ordinary organisms. Yet the trench is inhabited by fish, amphipods, bacteria, and other creatures specifically adapted to extreme pressure. These organisms have no air-filled swim bladders that would collapse. Their proteins are stabilized by special amino acid sequences and by molecules called piezolites that counteract pressure's effects on molecular structure. Their cell membranes contain unsaturated fatty acids that remain fluid under pressure instead of becoming rigid. The existence of Barophil's pressure-loving organisms suggests that life could exist in the high-pressure environments found deep within planets and moons. The subsurface oceans of Europa and Enceladus experience significant pressure from the weight of overlying ice. The deeper regions of these oceans, near the rocky seafloor, would experience pressures far exceeding anything at Earth's surface. Yet if Earth organisms can adapt to pressures in the Mariana Trench, alien organisms might adapt to even higher pressures in alien oceans. Some scientists even speculate about life existing in the liquid metallic hydrogen regions deep within gas giants like Jupiter, though the extreme temperatures and pressures there would require biochemistry completely unlike anything on Earth. Acidity represents another extreme environment where life flourishes. Highly acidic environments with pH levels below 3, comparable to battery acid or stomach acid, would dissolve most biological molecules and disrupt normal cellular processes. Yet acidophiles thrive in such conditions. Iron Mountain in California hosts drainage from abandoned mines with pH levels below 0, more acidic than concentrated sulfuric acid. Despite this extreme acidity, bacteria and archaea live in these toxic streams, deriving energy from oxidizing iron and sulfur. These organisms maintain neutral pH inside their cells while existing in incredibly acidic environments, pumping protons out of their cells faster than the acidic environments can push them in, a process that requires substantial energy but allows survival in places nothing else can tolerate. At the opposite extreme, alkalophiles live in highly alkaline environments, with pH levels above 9 or even above 11. Soda lakes like Mono Lake in California and Lake Magadi in Kenya have pH levels around 10, nearly as caustic as bleach. Microorganisms in these lakes have adapted to maintain their internal chemistry despite the harsh external conditions, using specialized proteins and transport mechanisms to survive. The existence of life in both extremely acidic and extremely alkaline environments suggests that pH is a challenge life can overcome through evolution, expanding the range of potentially habitable environments to include caustic lakes and springs on other worlds. Salinity creates osmotic stress that would kill most organisms. Normal cells placed in very salty water lose water through osmosis and shrivel up. Yet halophiles, salt-loving organisms, thrive in hypersaline environments like the Dead Sea, where salt concentration exceeds 30%, and in salt evaporation ponds, where salt approaches saturation. Some archaea not only tolerate but require high salt concentrations to survive. They accumulate potassium and other ions inside their cells to balance the external salt concentration, preventing osmotic water loss. Their proteins are specifically adapted to function in high salt conditions and would actually denature and unfold in normal salt concentrations. Hypersaline environments might exist on Mars, where briny water could remain liquid at temperatures below the freezing point of pure water. Salts detected on Mars's surface could create localized regions where salty water exists seasonally or sporadically. If life ever existed on Mars, or if it exists there today, it might persist in these briny environments, sheltered from the planet's coal-thin atmosphere by adaptation similar to Earth's halophiles. Radiation represents one of the most challenging extremes. Ionizing radiation damages DNA, breaks apart molecules, and creates reactive free radicals that wreak havoc on cellular chemistry. Yet radio-resistant organisms can survive radiation doses thousands of times higher than would be lethal to humans. The bacterium Deinococcus radiodurans can withstand radiation exposure of several million rads, enough to shatter its DNA into hundreds of fragments and completely repair its genome within hours. reconstituting functional chromosomes from the pieces. This organism accumulates high concentrations of manganese compounds that protect its cellular machinery from radiation damage and possesses redundant copies of its genome, along with extraordinarily efficient DNA repair mechanisms. The discovery of radio-resistant life expands possibilities for life in high radiation environments throughout the universe. Mars's surface experiences high radiation levels because Mars lacks a strong magnetic field and thick atmosphere to shield the surface from cosmic rays and solar radiation. Any surface life on Mars would need radiation resistance. The moons of Jupiter, particularly Europa, exist within Jupiter's powerful radiation belts and experience intense radiation bombardment. Life in Europa's subsurface ocean would be shielded by miles of ice, but any organism near the surface would need extreme radiation tolerance. Desiccation, extreme dryness, challenges life by removing the water necessary for biochemical reactions. Yet xerophiles can survive in nearly waterless environments. Microorganisms have been found in the driest deserts on Earth, in salt crystals, and even in the upper atmosphere. Some organisms, like tardigrades, microscopic animals also called water bears, can enter a state called cryptobiosis when they dry out. In this state, they replace water in their cells with protective molecules like trehalose sugar, essentially turning into a glass-like solid that can survive for years or decades without water, then rehydrate and resume normal activity when water becomes available again. The ability to survive desiccation suggests that life could persist in extremely dry environments like Mars, where liquid water is rare and exists only transiently. Organisms in a cryptobiotic state could wait through long dry periods, potentially centuries or longer, then reactivate during brief periods when liquid water appears. This strategy might allow life to survive, even on worlds where habitable conditions are rare and sporadic rather than continuous. Oligotrophs thrive in nutrient-poor environments where most life would starve. These organisms can extract energy and nutrients from resources that seem impossibly limited. Some bacteria derive energy from oxidizing trace amounts of hydrogen gas or from reducing tiny concentrations of metal ions. Others grow incredibly slowly, dividing perhaps once per century or even less frequently, living at the absolute minimum energy budget that can sustain life. These organisms survive in deep subsurface rocks, in ultrapure cave water, and in nutrient-depleted ocean regions. The existence of oligotrophs suggests that life could persist in environments throughout the universe that seem too resource-poor to support metabolism. Deep beneath the surfaces of planets and moons, in the pores between rock grains, organisms might eke out existence on trace amounts of hydrogen from water-rock reactions, or on the minimal nutrients leached from minerals over geological timescales. This greatly expands the potential volume of habitable space, not just surfaces and oceans, but the entire crustal volume of rocky worlds down to depths where temperature becomes prohibitive. Some of the most extreme environments on Earth combine multiple stresses. Hydrothermal vents on the ocean floor experience high temperature, high pressure, high concentrations of toxic metals and sulfur compounds, and complete darkness. Yet these vents support thriving ecosystems based on chemosynthetic bacteria that extract energy from chemicals spewing from the vents. Hot acidic springs combine high temperature with extremely low pH. Ice-covered Antarctic lakes combine extreme cold with high salinity and seasonal or permanent darkness. Life found in these multi-stress environments proves that organisms can adapt to simultaneous challenges, not just single extremes. This ability to tolerate multiple stresses simultaneously is crucial for evaluating habitability on alien worlds, where conditions often involve several challenges at once. Europa's ocean experiences cold, pressure, darkness, and possibly high salinity, all at the same time. Mars's surface experiences extreme cold, desiccation, high radiation, and low pressure simultaneously. Venus's clouds experience high acidity, moderate temperature, and the presence of sulfuric acid droplets. Each of these environments might seem impossibly hostile when considered as a whole, but examining them as combinations of specific stresses that Earth organisms have individually overcome makes them seem more potentially habitable. The extremophiles of Earth demonstrate that life is far more flexible and resilient than once thought. Organisms have evolved mechanisms to survive and thrive in virtually every environment on Earth where liquid water exists, at least transiently, and where some source of chemical energy is available. Temperature, pressure, acidity, salinity, radiation, desiccation, each extreme that seems to represent an absolute barrier to life, turns out to be merely another challenge that evolution can overcome, given time and the right selection pressures. These discoveries transform our search for life beyond Earth. Rather than looking only for planets with Earth-like conditions, moderate temperature, neutral pH, low radiation, abundant water, we can expand our search to include extreme environments throughout the solar system and beyond. Volcanic hot springs on Mars or Venus, frozen oceans on icy moons, the clouds of Venus, subsurface aquifers deep within asteroids, the hydrothermal systems that might exist beneath the surfaces of large moons. All of these become potential habitats once we recognize that life on Earth already thrives in analogous extremes. The extreme environments where life could thrive extend from the scalding vents of volcanic springs to the frozen lakes of Antarctica, from the crushing depths of ocean trenches to the desiccated rocks of the driest deserts, from intensely acidic mine drainage to alkaline soda lakes, from the radiation-blasted rocks near nuclear waste to the nutrient-depleted waters of remote caves. Each extreme habitat on Earth hosts specialized organisms that have turned hostile conditions into homes through remarkable biochemical and physiological adaptations, proving that life's potential territory extends far beyond the comfortable middle ground to encompass nearly anywhere liquid exists, energy flows, and raw materials can be found, vastly expanding the cosmic real estate where life might emerge and flourish across the universe.